Section 1.4 is pretty short and it's about conditional probability. So, for experiments with two or more events of interest, attention is often directed not only to the probabilities of individual events, but also the probability of an event occurring conditioned on the knowledge that another event has already occurred, which is why we call it conditional probability. Right? So, the probability that event A occurs given that event B has already occurred. So that's how we describe conditional probability, is the probability that event A occurs given that event B has already occurred. And the way that we denote that is the probability of A given B is how we would say this. This is A given B. This is the probability of A given B is how we say this. Okay, and that's A with a vertical bar and then B. So how do we define conditional probability? Well, let's have a look. The conditional probability of an event, it says even, sorry about that, of event A conditional on event B is here. The probability of A given B is equal to the probability of A intersected with B over the probability of B. Or if you want to think of it in quicker terms, the probability of A given B is the probability of A and B divided by the probability of B. And the probability of B will always be greater than 0 because we can't divide by 0. So it measures the probability that event A occurs when it is known that event B has already occurred. So often, like I said, this is read as A given B. So we're going to have a look. So this is our formula here, and we're going to have a look at how we might apply this. So for example, here we have, back to the same example we've been looking at in multiple sections. It says, let's look back here at our diagram from section 1.3, and we want to know what is the probability of event B. Well, if you remember, the probability of event B we found by adding up all of the probabilities inside the circle for event B. So everything inside of event B is what we're going to add up. And when we did that, we found that the probability of event B, which was the 0.07 plus the 0.19 plus the 0.04 plus 0.12 and 0.14, meant that the probability of event B occurring was 0.56. So we already found that in section 1.3 when we were in class together. But if we know that event B definitely has already occurred, what is the probability that event A also occurs? So that would be the probability of A given that B has already occurred, which is the probability of A intersection with B divided by the probability of B. And we know that the probability of A given B is what we find in our, what we like to call our little football here in the middle. So this is A given B. So here, or sorry, not A given B, sorry, A intersected with B. So our probability of A intersected with B would be 0.07 plus 0.19 divided by the probability of B, which we said was 0.56. So we end up with 0.26 out of 0.56, or a probability of 0.464. So our probability of A occurring, given that B has definitely occurred, is 0.464. Let's see if we can apply conditional probability given a couple of different games of chance. So these are things like our dice and our cards and things like that. So example 1.4 Point 2a says your friend rolls a die and tells you that the result is even. What is the probability that your friend rolled a number less than 3? So we have to think about these as two different events, right? So if event A is that your friend rolled an even number, let's define A as the even number, which means that A is the set 2, 4, and 6. And then that also means that we now have to define event B. Well, B would be less than 3, right? Less than 3, which means event B contains the outcomes of just 1 and 2. And in order to find conditional probability, we're also going to need to know the probability of A intersected with B. So we're going to need to know then, what is A intersected with B? We have an even number, right? An even number that is less than 3. And that is only going to be the element A intersected B is only going to have the element 2, because 2 is the only outcome that is both even and less than 3. So let's talk about our different probabilities, right? The probability of A occurring is 3 ways out of 6. The probability of B occurring are 2 ways out of 6. And the probability of A intersection B is only 1 way out of 6. So if we won't need all 3 of these to do our conditional probability, but we can see the different parts that are moving now, because what we're saying is, what is the probability that your friend rolled a number that is less than 3, given that we know they already rolled an even number? So that would be the probability of B given A, which would be the probability of A and B's intersection, or B intersected with A, divided by, switch colors here, divided by the probability of A. There we go. So the probability of B intersected with A, or A intersected with B, right, we can say this is the same as the probability of B intersected with A. Those were part of our established rules that we set early on, is that it doesn't matter which order as long as they're both there. And we know then the probability of B given A is 1 over 6. And we know that the probability of just A is 3 out of 6. So our probability of B given A is just 1/3. So the probability of B given A is 1/3. And you can also think about it as this one, you can sort of think through it logically. What are the ways that you can roll an even number? There are 3. And out of those, how many are even? Just 1. So you only have 1 way out of all 3. So if you define your events a little differently, you can usually figure out a way to make it make sense outside of having to use conditionals sometimes. But in this case, I wanted for us to see how to use it with conditional probability. Well, let's up the ante a little bit, no pun intended. And we're going to roll 2 dice now. 1 red die followed by 1 purple die. What is the probability that the red die resulted in a 6, given that at least 1 6 was already rolled? Okay, let's remind ourselves that our first roll is red, and our second roll is the purple. Okay. So it says, what is the probability that the red die resulted in a 6, given that at least 1 6 was rolled? So let's define event A to be our red 6. Right? Red die resulted in a 6. Let's call that event A. So let's define the sample space for event A. The red die resulted in a 6. Remember, we're rolling red first, so that means we have the set 6, 1, 6, 2, 6, 3, 6, 4. Oops, there we go. 6, 5, and 6, 6. So there are 6 ways to roll a 6 on the red, right? So it could be a red 6 with a purple 1, 2, 3, 4, 5, or 6. Fairly straightforward. Well, what if we let event B say that at least one 6 was rolled? Well, event B then not only has 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, but it also has 6, 1, 6, 2, and I suppose we could have put the 6, 6 there. We could have had 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and then lastly 6, 6. So we have 11 total ways for event B to occur. Now the question really says, where do we have a red die that is a 6, and it means we have at least one 6? Well, that would be where we have a 6, 1, a 6, 2, a 6, 3, a 6, 4, 6, 5, or a 6, 6. So we need to define A intersected with B. So if we find the sample space of A intersected with B, it ends up being a 6, 1, a 6, 2, a 6, 3, a 6, 4, a 6, 5, and a 6, 6. Because that means that our red die was a 6 and we got at least one 6. So that's all of our events in A intersected with B. So then the probability of A given B, so A given B would be the probability of A intersected with B divided by the probability of B. And in this case, it's kind of an interesting one that'll lead us into the idea of independence. Because the probability of A intersected with B, we have 1, 2, 3, 4, 5, 6 opportunities or 6 possible events out of 36 possible rolls. Because remember, we have 6 options for 1 and 6 options for 2. So we would go from everywhere from 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 through 2, 2, 1 through 2, 6, 3, 1 through 3, 6, etc., etc. So we'd have 36 different rolls. And we outlined this before in a previous section, just a reminder. And then for B, event B, we only have 11 possibilities out of 36. So all told, our probability of A given B, so the probability that the red die resulted in a 6, given that at least one 6 was rolled, is going to be 6 out of 11. So we have a 6 in 11 chance that rolling our red followed by purple will give us a red die, resulting in a 6 if we know that at least one 6 was rolled. Let's try one last one. So this last example says you flip 2 coins. What is the probability that 2 heads are flipped given that at least one head was flipped? So once again, we find ourselves in this situation where we have event A would be 2 heads are flipped, event B is at least one head was flipped. And we want to know, right? We want to know then what is the probability that two heads were flipped, A, given that we know at least one was flipped, which is B. So we're looking for the probability of A given B. So let's define sample set A. So the only way that we can flip two heads is literally just that one combination of just head, head. And remember, our total sample space is head, 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 tail, tail, head, and tail, tail. So for B, our event B, at least one head was flipped. Means the only way that doesn't happen is if we get tails, tails. So there should be three opportunities. We'd have two heads, we'd have a tails, heads, and we'd have a heads, tails. And then what we need for the last part is where they overlap. So A intersected with B, right? Well, that would just be a heads, heads. It's the only element they have in common. So let's look at our probability of A given B. That would be our probability of A intersected with B over our probability of B. And in this case, the probability of A intersected with B, there's only one way out of four possible outcomes to flip a heads heads. And the probability of B, we have three ways out of four, so we end up with a chance that is 1 in 3 that two heads are flipped, given that at least one head was flipped. So we're up at 1/3.